right, so like I said, we are looking at systems of linear inequalities. So we are basically taking what we did in 2.8, which was the quiz with the solid and dashed, shading above and below. And we're taking what we've been doing in 3.1 and applying them together. So now we're going to be graphing two lines, but our lines are going to be back to being solid and dashed and have shading. So we're taking basically 2.8 and 3.1 and meshing them together. So part of that is understanding inequalities. So go ahead, take a minute and solve for x in both of these examples. And remember that if you divide by a negative, your inequality changes direction. So go ahead, take a minute and solve for x. What, honey? Right by the door. Right? So when we do that, over on the left, we have 5x is greater than 33. Divide both sides by 5, and we get x is greater than 33/5. And on the right, you had two choices. You could have divided both sides by -5 to start, changing the direction of the inequality. You could also have distributed the -5 and then added 5 and then still just divided by a negative value and ultimately simplified to x greater than -7/5. Okay, so then what we're going to do is go back to lesson 2.8. We're going to practice graphing inequalities. So in order to graph an inequality, what you want to do is start with your y-intercept. So in this case, we're going to start our graph at -1. So you plot your point at -1, and then you're going to apply our slope. So my slope is 4. So we're going to go up 4 and over 1, up 4 and over 1. You could also go down 4 and left 1. This line is less than or equal to, but nonetheless, that implies that my line is solid. So I'm going to draw in a solid line connecting those points. And my y values are less than this line. So where are the y values less than? Well, the y values are less than below the line. And over here, we're not quite in the form we want to be in, so we're going to divide everything by 3. So that gives y is greater than or equal to 6 divided by 3, which is 2x, and 3 divided by 3, which gives a positive 1. So we get y greater than or equal to 2x plus 1. thus making my y-intercept a positive 1 and my slope a positive 2. So we're going up 2 and over 1, or down 2 and left 1. And once again, my line is solid because it is greater than or equal to. So we connect each of those points with a solid line. Now my y values are greater. So where are the y values greater? The y values are greater above the line. So very similarly to solving systems of equations and to solving linear inequalities, to solve a system of linear inequalities, we're going to start by graphing each of our lines in the form y equals mx plus b. From those graphs, we are going to shade our lines following the inequalities being greater than or less than, as well as determine if my lines are solid or dotted. So again, they are dotted if my inequality does not include the equals. If it is equal, then the line is solid. It's above for y greater thans and below for y less than. So all of the rules from 2.8 apply. Okay. So let's look at some examples involving linear inequalities. So as I previously stated, we want to get each of our equations into y equals mx plus b form. So what we're going to do is rearrange the terms so that the y value is solved for. So in the red equation, all I have to do is add x to the other side. So you have y greater than a positive x minus 1, making my y-intercept negative 1. My slope is positive 1. Now in the past, I only had us really focus on getting like 3 points. This time, with graphing systems, we really need to make sure we shade and graph one of our lines completely. So for y greater than x minus 1, I want to make sure that I can fully see that dotted line in its entirety. If the y values are greater, I am going to shade above. So what I like to do is after I graph the first equation, I lightly shade, or I just put some slashes so that I know where the shading is for the first line. Because what we need to do is understand, but my solution is not all of that red space right now. The solution is going to be limited to the overlap of the two equations and their solutions. So now I have a light shading for the first equation and its solution. I'm going to get my second graph, which is y greater than negative x plus 3. So my y-intercept is at +3. My slope is -1. So this graph is going down 1 and right 1. Or up 1 and left 1. It is also dashed, which means solutions do not come from the line. The y values are greater than, which means we shade above. So the solution to these systems of inequalities is only the overlap. It's this upper triangular region that is in purple, because red and blue make purple. So this triangle up here needs to be ultimately the darkest shaded region on your paper. I've also had students that just don't shade at all. So you don't have to have this red or blue shading over here. Or maybe you have just the blue, or maybe you have just the red, so that I can see that okay, this one might be here and here, but they overlap here, so this is darker. Everybody understand and okay with that idea? That this has to be the darkest? All right. Let's look at the next example. So what's nice about this example is that the first equation is already in slope-intercept form. So I'm going to plot my y-intercept. I'm going to apply my slope. My line this time is solid. The y values are less than, so I shade below. And then I'm going to shade my blue line. So that blue equation is a vertical line. The slope of a vertical line is undefined because it's only going straight up and down, no left to right. So it goes through x equals -3. My line is dashed. And x values are greater than. So the x values with respect to this line are bigger to the right side of the line. So I'm going to shade to the right, which is over here, which means that my solution is this triangular region between the red and the blue. That means the points in here and on the red line are my solutions. Can I pick a point on the blue line? Can I pick the point where the two lines overlap? No, because the blue line is dashed. So that was kind of a trick question in a sense, because our solutions to two intersecting lines before was a solution. If the blue line was solid, then yes, you could pick the point where they intersect. Because the blue line is dashed and the red line is solid, the point where they intersect is not a solution. So this point at I think it's -3, or +10 is not a solution. So once again, let's graph our lines, but in order to graph them, we want to put them into our standard form. So for this equation here, we're going to divide everything by 6, thus giving y less than or equal to -4 over 6. Now you can reduce that fraction if you want. X minus 24 divided by 6, which is 4. So my y-intercept is at -4. My slope is -4 over 6, which is the same as -2 over 3. So you can go down 2 and write 3, or you can go down 4 and write 6. You're just going to get half the points I get. This line is solid. And the y values are less than, therefore we shade below. We're going to solve the second equation for y. So we're going to divide everything by 3. So I get a y-intercept of +1. My slope is -2/3. So what do you notice about the slopes of these two lines? Good. Yeah, my slopes are the same. Both lines are solid. If my slopes are the same, they are parallel. So in order to have a solution, the green line either needs to be shaded below, but because the green line is shaded above, does my shading overlap? No. Exactly. So it's no solution. If you graph two lines and the shading does not overlap, then it is no solution. Because what that means is that there are no points that make both equations true. And the whole overlap of the concepts and the graphs is that where they overlap make both equations true. Good. Yeah. Yes. It's a whole bunch of them again. Yep. Right. So, or I could say something like, give me, not on this example, because obviously the shading, but for this one, I could say, give me an solution to both. And that would be any point in that shaded region. Exactly. So like you could say 0, 0. Somebody else might say like -6. Well, not -6, 0, -6. So yes, there are like the number of solutions is not infinite in a way because there are spaces that are not solutions, but there are infinitely many solutions you could give to these equations. Right, there is, yeah, so like this one, the point of intersection is right here at 2, 1, but 2, 1 is not a solution because both lines are dashed, exactly. So that's still your point of intersection, it's just that that point of intersection is not a solution. Where in the previous lesson, the point of intersection was the only solution. Okay. So your homework is that next page, right? Because we finished all our examples. Okay. Your homework is the front and the back of that next page. Remember, if it's an X or a Y, it's either horizontal or vertical.